Welcome to today's webinar. The topic today is steel joint design in RFEM 6 using practical example. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the technical content of the website, German and English webinars, customer projects, newsletters, and so on. I will be the moderator today and also the presenter. My colleague Walter Fröhlich will support me and he will answer your questions. He's responsible for customer support and also for the product engineering. He's the main responsible person for the steel joints add-on. Okay, I say some words how you can ask questions. At first, I switch off my camera that you can see the full screen. You can click that button here. Then you can enter your question here, press send, and Walter will receive your question and he will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, I will model different connections. I start with a base connection, then rigid and pinned connections. Then follows the connection design, and we do a stiffness analysis. The third point or fourth point is result evaluation and documentation. And the fifth point is prospect. Okay, that's the model for today. Larger carport. The dimensions are 6 meters by 7.5 meters. I display two guide objects. Just a moment. Visual objects. I activate them. Two cars that you can estimate the dimensions of the carport. That's the reason why it's made of steel. It's a little bit larger than a normal carport. Okay, I deactivate the guide objects. So we have different load cases, self-weight load case, snow, wind in all directions. Then there are different load combinations, ultimate limit state, and for the serviceability limit state design. Also load combinations for the design of lifting up. Okay. So then I did a steel design. Design ratios by members. All designs are fulfilled. With larger and higher design ratios. Okay. Then we activate the steel joints add-on in the base data add-ons. And steel design is already activated, and we activate steel joints that we can design all the joints of the structure. So standards, we use the Eurocode and the German National Annex for all for the load cases, classification, and the combination wizards for the steel design, and also for steel joints. Okay. So then we start with the first joint. I right click on that node and I choose create steel joints. It's only one member. The type's ended. Now that's clear. Maybe we turn back to main. Yeah, let's check the ultimate configuration. That's default. You can perform a buckling analysis. Yeah, if you have larger plates, such as webs or so, yeah, then you can also perform a buckling analysis. That's quite important. The design check for the plates, the limit plastic strain is 5%. Also for the welds, yeah, you can change that, yeah, but I'll leave that because that's the value from the Eurocode standard. Okay, I'll leave also all the other settings. Then we turn to components, and I can press insert component at beginning or at end, that doesn't matter. But I select this component, base plate. Now we have different modifications, stiffening elements, connection elements, and others, where also the fasteners. Yeah, you can move with the mouse over the image, and you can see as a tooltip what connection or what stiffening element is available. So I select base plate. That looks already quite good. That's a concrete block. We decrease it a little bit. Let me enter some values. The thickness of the plate should be 10 millimeters. Top offset in all directions is 10 millimeters. To overtake the previous value, you can press F8. F8, F8, F8. Then we have the value on all sides. So then the thickness of the concrete block should be 200 millimeters. And I define the offset again. Also a very small offset of 10 millimeters. I overtake it again with F8. So then you can consider cracked concrete. Yeah, we do that. You can also consider edge reinforcement, dense reinforcement, grout. You can display that grout. No, we don't use a grout. Then you can consider the shear transfer by anchors, and you can also consider friction if you want. So then we turn to the anchors. M12 is okay in our case, and we choose 4.6 for the strength grade. So these dimensions are okay, this distances. Then we change that value that it's exactly in the middle. The shear plane shouldn't be in flat, and we choose or we consider the reduction due to cut thread. So the height or the length of the anchors should be 100 millimeters. That's okay. And the welds are also okay. Yeah, that was very quickly. That's all for this joint. We do the plausibility check. That's okay. We take a look at the model. Now you can see the joint or the column-based joint here. You can disable it when you press no joint model, or you can display the simplified joint model. right above here. But we would like to display the detailed joint model. So I double click on the steel joint again, and I assign also the other nodes right above. So this one and this one and this one. Okay, now where are all 4 nodes selected? So the next joint is the frame corner. Yeah, we can see in the model, the steel model is stiffened in all directions by frame corners. In this direction, also in this direction. There are no bracings. And we would like to define the connections on the frame corner. So I show you another way to do that. You can see in the navigator data the types for steel joints. One steel joint is already there, and I can do a right click and press new steel joint. But now I have to assign the node. Okay. So for members, those 4 members are connected in that node, and we would like to do a stiffness analysis for the frame corner. So that's why I select initial stiffness, no interaction. Let me go to the settings. Initial stiffness is selected. For the future, there is another stiffness analysis type available, or there will be another stiffness analysis type available, the stiffness diagram. Yeah, that's for larger connections with high loadings. Then you can consider the plastic behavior. Then in the future you can select generate hinges in global model. That's not yet available. That's why we do that by hand later. Okay, that's all. So we turn to members. At least one member should be supported. Let's end it. This one is continuous, and automatically the member 3 is also continuous is selected. So for the column, we would like to do a stiffness analysis. The program should calculate the stiffness of the joint in or around M and around Z. Means M, Y and M, Z. And for this horizontal beam, there should be also a stiffness analysis M, Y. Okay. So then we turn to components. We insert a component and this time an end plate. You can move over it, end plate in the middle. So the connected member 1 should be the column. You can see it's selected in the right window with the yellow selection. And the reference member should be the member 2 and the member 3. Okay. So you can already see a connection. Now we have to modify it with the next steps. So the thickness of the plate should be 15 millimeters. the offset in this direction should be 60 millimeters. Also in the other direction. And in this direction, there should be no offset. You can see the changes in the window and anytime. So M12 is okay, but we choose 10.9 as strength grade. So that's okay, all those distances, but we select also for the spacing vertically 2, and I select these values, and that's looks quite good. We use preloaded bolts for this connection, and the shear plane shouldn't be in flat. And I changed the welds for the flanges to 4. Okay. Now you can see anytime what parameter should be defined. So that's all for the connection of the column to the horizontal beam. And now we would like to connect this horizontal beam with this horizontal beam. Okay. That's why we insert a component from the library. So I select that. And what's quite new, the library is in the Dlubal Center. Now you can see different template types, also user-defined from me. So I select only the defined connections or joints by Dlubal Software. We've got the I section. The connection is bolted. And there are 3 members in the connection. So, and we would like to select end plate to plate. That looks quite good. So I double click on it. So and we should see a preview in some seconds. So, but at first we have to select the member that should be connected, be member number 4, this horizontal beam, to member 2 or to the members 2 and 3. The preview looks quite good, and we can overtake it with OK. So let me change the values. Also a thickness of 15 millimeters. No, we have to select that line. Thickness of 15 millimeters. Okay. Minus 7.5 is okay. That we can consider a weld here. Okay, all the values for the end plate 1 is okay, but we have to modify the reference plate. 15 millimeters. The top offset and bottom offset is okay, but now I decrease the width that we have the same dimension as the end plate. So it should be stiffened. Okay, but not on this side, because we would like to define two stiffeners here in the back, but we can't do that because the connection would be closed. So center is okay, but not both sides, only one side. So now this stiffener is disappeared. Okay. So then the diameter should be M12, 10.9 as strength grade. So let me change the spacings. 53, 35, then also here 35. Okay, so preloaded bolts and the shear plane shouldn't be in thread. The welds are okay, 5 millimeters for the flanges and 3 millimeters for the webs. Okay, so then we have to add the stiffness here. I insert a component at the end. You can see the stiffener here. The stiffened member should be this one, the horizontal beam, and the reference member should be the column. So then position is okay. And you can say perpendicular or parallel. Sorry, that was a wrong click. So that looks quite good. But it shouldn't be on both sides. You can see that would be closed here. That's why we select the right side. Then we have only the stiffness on this side. Okay, so the welds, the welds for the stiffness are okay, 3 millimeters. Plausibility check is okay. I can select also the other frame corners. Okay. Plausibility check is okay. And we can display all in the model. Okay, that looks quite good. Then we add joints for the purlins. I do a right click, create steel joint. So then members are, those are the 3 members. This one is supported and also continuous. And member 3 is also continuous. So then component. At first we enter a cap plate at the end. Not that we create a gable support. So yeah, beginning or end, that doesn't matter. And you can see the cap plate and the second line in the middle. So this isn't member, is member 2, that's okay. 10 millimeters is also okay, but I define a top and bottom offset of -5 millimeters. Yeah, that we can weld that here. So then that's now in the middle, and we can select or we can define an actual displacement that we move it to the end. So that looks much better. So then welds for the flanges and for the web, 3 millimeters. That's okay. So and now we have to add fasteners. We insert component at the end. So and you can see in the line below others, and there are the fasteners. So the component 1 is a plate, a member plate. Yeah, a plate is, for example, that cap plate or an end plate, and a member plate is a plate of the member, the flange or the web. Yeah. So that's why we select member plate. I zoom a little bit in. So and then at first we select member 2, flange 2. Yeah, you can see it in the preview what is selected. Member 2, flange 1. Should be connected with member plate and the upper flange. Okay. M12 4.6. Then in this direction only 1, and this direction 2. Yeah, and now it's in the middle of the member. I enter 35 millimeters, and you can see now the bolts are okay. I changed that value 25 millimeters. Okay. No preloaded bolts, and the shear plane shouldn't be in thread. Okay, that's all for this connection. Plausibility check is okay. We select the other inner purlins. The connection doesn't fit for the purlins at the edge because of the bolts here. So plausibility check, it's okay. So and we can take a look at all the connections. That looks good. So now I turn back with double click in this dialog, and now I copy that connection for the outer purlins. So at the bottom on the left side, copy selected joints. So at first I have to select the other nodes. So 4 nodes. Okay. And there should be an error message, wrong position of the fastener. That's what I mean. Okay, we have to enlarge the horizontal member. So how to do that? We insert a member cut at the end. Left above, member cut. It's also, you can cut a member or you can increase the length of a member. Member to cut is member number 1 by member number 2. So, and not the closer end, but the farther end. You can see now the length is okay. So now should also the plausibility check okay. Yeah, that's all. Okay, now all connections of the model are created. Let me go to the load case imperfections in the navigator data, right click, load cases and combinations. And let's move to the design situations. Ultimate limit state design, the steer design and the steer joints design is activated, that's okay. Serviceability limit state design, only steer design is selected, that's also okay. And for this design situation, EQU, also both designs are activated. So to skip the calculation time, I turn to an already calculated model. So in the table below, we can take a look at the steer joint design. I turn to the table design ratios by joint. So, and you can see on the right side the design check types. I overtook the model from the German webinar. There are some German words, but that doesn't matter. Take a look, please, at the design checks. For that's the anchor check, the concrete check, for the column-based connection, the plate check of the frame corner, the ultimate limit state for the pre-loaded bolts, the filled well check. I double click on that line to go to the details of the check. When it's opened the first time, it takes some time, not in the second step. So you can see the design check for the welds. And you can also print that in the printout report. We will do that later. So let me check the preloaded bolts. You can double click on that line, or you can click on that button, design check details. Might take also some time. So, and you can see the equations from the standard, also where you can find it in the standard, tension resistance, punching shear resistance, and so on. Okay. For the frame corner, we have quite high design ratios for the fasteners and also for the welds, and a lower design ratio for the plate check. but you have to consider that's only the comparison with the plastic, of the limit of the plastic design. So I double click on it. You can see, that's the value from the standard, the limit equivalent plastic strain, 5%, and we have a quite low equivalent plastic strain in our model. Let me check it in the steer joint. You can click left above results in steer joint. So, and I press that button here, consider specific component, and you can see for this design check what plate is considered. That's the lower flange of the horizontal beam. And you can see a very small area where you can find a plastic strain. But we have, of course, I can show that we have also elastic stresses. I check here equivalent stress, and you can see also the elastic stress. And also only in this area where is a small plastic stress, and that means also a plastic strain. And but why we have such a low design ratio? I can explain that with a slide in the PowerPoint. So that's the material model, and as long we have only an elastic stress, where is a design ratio of 0, because we compare the plastic strain. In our model we have a small plastic strain, and we consider that with the maximum plastic strain, that's the value from the Eurocode, the 5%. That means you can't increase the load with a factor 5 or so. That's not possible, because that's the area of the plastic strain, and but we have got already an elastic stress and elastic strain in the model. And if we increase the load a little bit more, then it would be quick. We would get quick a higher design ratio. Okay, I turn back to the model. So let's take a look at the stiffness analysis. Those are the rotational stiffness values for the frame corner. Those are the values from member 1 for the column, and those are the values for this horizontal beam. And we have to overtake that values by hand. So we start with the columns, the column ends. We overtake these two values. So we take here the smaller value. So I double click on the member. I select hinges, and we turn to the dialog hinges, and we need to consider member hinges at the end. So the rotational spring constant should be, can move it a little bit higher, or I close it again, sorry. I move that dialog a little bit higher. You can see the rotational stiffness is displayed here in meganewton meter per rad, and I have to enter it here in kilonewton meter per rad. So that's why I have to multiplicate it with 1000, 6400, and in this direction 1400. Yeah, this value is here, and this value is here. Okay, so at all member ends. So now you can see the hinges here. So the same for the horizontal beams. Double click, hinges. I turn to hinges and enter hinges for MY 2800. Okay, the member start and the member end. Okay, so all member hinges are created, and then we can calculate the model again. I skip the calculation time and turn to an already calculated model. Let me check the steel joint design. So all design ratios are under 1. That's okay. I turn to the steel design ratio by members. And you can see the maximum design check is for the serviceability on that point, and that was quite lower in the original model. Let me compare that in the PowerPoint. The design ratios for the ultimate limit state design are nearly the same as in the original model. Differences of maybe 1 or 2% occurred, but for the serviceability limit state design there are larger differences. You can see that in the PowerPoint. So that's the check criterion serviceability limit state with consideration of the connection stiffness and without and with. So you can see the connections here and the stiffnesses are considered. So, and you can see for the frame in this direction, there was an ultimate limit or design ratio of 0.27, and now we are 0.3. A small increase also for the horizontal direction from 25% to 29%. But for the frame in this direction, that's the same direction as the purlins are, was without consideration of the connection stiffness 56%, and now we are 94%. That means you need to consider the connection stiffness of your model. It can be that you have higher design ratios for the serviceability limit state design, and also for the serviceability limit state design, as we had or have in our case. Okay, I turn back to the model and we turn to the next point for today, for the documentation. I would like to print detailed results. For example, of one connection, steel joint design, I used a preloaded board check. Let me open the design details, and I would like to print the equations from the standard and the design in the printout report. So those equations should be displayed in the printout report. That's why I print graphics, or I print it to the printout report. So this is the printout report. I leave the settings. I uncheck the steel design for our webinar. We printed steel joint design ratios on steel joints by steel joint. That's quite okay. I press save and show. So the printout report is creating. So general settings are, for example, for the cover, I can do a right click, edit. I can enter the client here, John Doe. You can check the preview image or display the preview image. Okay, I have increased that value for the printer. So, okay. Then let me find the equation or the detail check. What was printed here. I can also move that at the end of the printout report. So, and I would like to print another graphic as an example. So let me move that to the other screen. So I leave that dialog and I double click on the column-based joint components. So, and then I select the view in +Z direction, and with a right click I can add new dimension. For different dimensions I select linear. So in X direction. So, and I select the corners of the plate and the concrete block and the bolt. So then in vertical direction the same. Okay. So we can also display the values not in meters but in millimeters. Left at the bottom we can change the units. So for the dimensions from meter to millimeters. Okay, so that looks quite good. I apply that and print it in the printout report. So the printout report, okay, then maybe window filling, the rest of the settings are okay. So, and I press OK because the printout report is already open. So I move it to that screen again. You can see under types for steel joints, you can see the graphic. I move it also to the end of the printout report. So, and now let me check the steel joint design settings, the objects to design, situations, the settings, then classification, stiffness analysis. So, and here the design ratios on steel joint by joint. Okay. So, and at the end, we have the details of the check and the graphic. Maybe some general features. You can print the printout report in a PDF or export it to an HTML file. You can translate the printout report. Or it would be translated automatically into 10 languages. Okay. That should be all for the documentation. Let me turn to the last point of the webinar. I turn back to the PowerPoint slide. Those are the planned features. We have released the component surface contact, and we will also release the line contact. That's a stiffening pressure contact. We plan to release the joint structure interaction. That's an automatic generation of the hinges with the associated spring stiffnesses. That we did manually in this webinar. I also mentioned already the new stiffness analysis stiffness diagram, where as a consideration of nonlinear stiffnesses under larger loads. Then design of connections with result members will be available. Then creation of concrete block in component fasteners. Just imagine you would like to connect the flange to a concrete wall, and that would be possible. And the last of today mentioned planned features are the connections with massive cross sections. E.g. round steel. Okay. That's all for today's webinar. Just a small hint, you can book your free online appointment, such as a product demonstration for our products, RFEM, RSTAB, our wind, our section, or to the add-ons. Just contact our sales team with that link, or you can scan that QR code. In the next days, you will get an email with your attendee certificate, with the link to the website, with the PowerPoint, with the recording, and with the model. Okay, thank you for your attention. I wish all a nice rest of the day. Thanks to Walter for answering the questions. Bye-bye.